Hi, everyone. I made it. So I was going to translate the entire talk into Polish last night, but I got drunk instead. So thank you. But seriously, thank you for having me. I'm super excited to be here. I'm super excited to deliver this talk, and I really hope you enjoy it. So the title of this talk is Taming the Modern Data Center. A little bit about me, for those of you that don't know, that's me. I hail from Pittsburgh, Pennsylvania, which is way on the other side of the pond. I had quite the travel ordeal getting here. If you want to ask me about it later, go for it. That's my Twitter handle and my GitHub handle, so feel free to tweet at me if you have any questions. I have direct messages open, so if you have a question that you don't want to ask publicly, you can ask me, even if I don't follow you. I'll probably follow you anyway. And if you ever want to bring me in on a conversation on GitHub, feel free, or just say hi. So a little bit about me. I work for a company called HashiCorp. How many people have ever heard of HashiCorp? Awesome. So for those of you that didn't raise your hand, we make a couple open source projects. Vagrant, which is a command line driver for virtual machines. Packer, which is a tool for building automated machine images. Surf, which is kind of the underlying layer console, which is used for gossip-based protocols and service discovery. Terraform, which is a product for I'll talk about all these in depth more in the talk. Terraform, which is a product for configuring and managing basically infrastructure as code. And most recently, the logo's not on this slide, Vault, which is a tool for managing secrets in an organization. So this talk is about the modern data center. And in order to talk about the modern data center, we kind of have to take a step back. So I want to go back in time and ask ourselves, how did we get to this notion of a modern data center? Or what is my definition of the modern data center? Because it may be different from yours. So how did we get here? Well, back in the day, and when I say back in the day, I mean 20, 30 years ago, we lived in the era of mainframes. And mainframe operators were in a very large room with a very large machine that made very funny noises. And that was how we ran applications. It was very expensive, not only to maintain them, but to build them. So mainframes originally were restricted to organizations that had a lot of money, so big enterprises and government. That's where we first saw a lot of the compute capacity. Well, shortly after that, as Moore's law applied, we got those mainframes down into smaller machines, smaller servers. We could rack them, we could network them, and we have kind of the notion of the data center like 10 years ago, which is a whole bunch of servers, lots of blinking lights, lots of cables, but everything runs on bare metal. So every machine has a certain number of resources. You know, they have 50 megabytes of RAM, and that's what that machine has. Well, about 5 or 10 years ago, we entered the era of virtualization, and we have tools like VMware and Parallels, VirtualBox that allow us to run a machine within a machine. And at the same time, those physical machines in the data centers grew in capacity. So we could add more memory to them, we could add more disk space. We have SSDs, which are faster hard drives. We have better IOPS. And now we can run 10 machines on what normally we could run a single machine. So we effectively increased our capacity. And now in the last 2 to 3 years, we throw containers on top of that. So tools like Docker or LXC, Solaris Zones, BSD jails, these tools that have been around for a while are now gaining popularity because the technology allows us to use them effectively. So how many people here are using containers? Okay, how many people here use virtual machines, whether it's for production or local development? Cool. How many people run on bare metal? Yeah, there's a lot less hands going up. So very few people run on bare metal. If you're running on something like a public cloud like EC2 or Google Compute Engine, you're not running on bare metal. You're running on a virtualized environment. It gets more complex because now we have companies that provide services for us that we used to provide on our own. So things like DNS, CDNs, email providers, external databases. We outsource those because sometimes it's cheaper to pay a company to manage a Postgres database than it is to hire a PostgreSQL admin to maintain your own. And even worse, we have this hybrid notion in some organizations where Your production infrastructure is on bare metal because it needs to be or it's always been, but then your staging or your development happens in some type of cloud-based environment. And you need to be able to handle both of those environments at the same time. They need to be as close to each other as possible so that your staging is as close to production as possible. So in reality, this is a lot what the modern data center looks like. It's this conglomerate of physical machines, containers running on VMs, VMs running on physical machines, communicating with external services that run in the cloud or are hosted by some other organization. And those external things I like to call the IaaSes, the IaaS, the PaaS, and the CS. The infrastructure as a service, platform as a service, software as a service. Modern technology has allowed companies to build businesses around providing technology as a service, whether it's a product or something like Heroku, which gives you like machines as a service, or EC2, which gives you virtual machines as a service. And we have certain other restrictions too, like there are certain things that can only run on OS X, right? You can only build iPhone apps on OS X. So if your company is producing iPhone or iOS apps, you have to have some type of Apple hardware in your data center, or you have to rent it from someone, right? Or if you're running accounting software, you probably are running it on Windows. And I think the majority of everyone else is running things on Linux. So depending on your infrastructure, you now have not only a hybrid cloud in the sense that you have containers and VMs and physical machines, but you also have different operating systems. And Windows behaves very differently than OS X, which behaves very differently than Linux, because OS X is based on Darwin and Linux is based on a completely different kernel. So let's talk about taming this, because a lot of times it's very difficult to rationalize what is going on, especially as data centers rise in complexity. We stop talking about physical machines, so we stop naming machines like, this is the file server 1, the file server 2. And we start giving them random IDs, we start aggregating them, and we start talking in percentages. So we only care about a certain percentage of the file servers being available. So in the past, I want to talk about the APID cycle. And this is, again, for history. So in the past, when you wanted to acquire a new machine, so if you wanted to add a compute engine to your cluster, this is what you had to do. You had to acquire the machine, provision it, update it, and then eventually destroy it. The acquisition stage involved picking up the phone, calling a hardware vendor, someone like Dell or IBM, who was making physical machines. You would purchase order it. It would arrive 6 to 8 weeks later in the mail. From that point, your data center operations team, the people who worked in your data center, would unpack that machine, take all the little fuzzies out, unwrap it, put it in a rack, plug it in, turn it on. Then your sysadmins would take over and they would provision the machine as necessary. So if this was going to be an application server, they would install the application, they would install the necessary users, the packages, etc. And then 2 to 3 years later, when that machine was ready to be phased out or the application lost all its funding, you would destroy it and re-provision it and go through this whole cycle again. The problem is that took a lot of time. If you got a burst of traffic, you couldn't auto-scale, because auto-scaling takes like a month in the APID cycle. Well, presently, we have a lot of the elastic compute and the IaaS era. So elastic compute helps with the outer edges. So elastic compute allows us to take the acquisition and destroying of a machine down from weeks and days to just a few minutes. So if you try to spin up an EC2 instance right now, you could probably have it spun up by the time I advance the next slide. And destroying it is really just one command. Same thing is true if you're running on like bare metal with OpenStack or something like that, your own private cloud. We can acquire and destroy instances effectively immediately. This allowed businesses to shift their expenses from capital to operational. So no longer did we need to spend millions of dollars on physical hardware because we could virtualize it. Now we have to pay people to manage it. And that's what caused the rise in the proliferation of the IaaSes, the softwares as a service, the platforms as a service, infrastructure as a service. And those tools were powered a lot by configuration management. So configuration management allowed us to take the provisioning and updating of machines, of nodes, down from days to just a few minutes or even seconds in some cases. So we captured our configuration using something like Chef or Puppet or Ansible or Salt, and we could deploy that across 1,000 machines at one time, and they were all identical. And we could iterate on that very quickly, so adding a new user was just one simple step. This is what caused basically the SaaS proliferation to happen, what I call specialized.com, which is where we see a lot of these businesses that have very specific technological like processes. They do one thing. They do it very well, but they do one thing. And that's important because you have to compare that to what we used to have, which is everything is in-house, everything is managed in-house. And now we're talking to external services. So all of this really begs the question, given a data center that is highly complex, and when I say data center, this very well could be running in a virtualized environment. We have physical servers, we have virtual machines, we have containers running on virtual machines, we have containers that can run on bare metal. And that data center needs to talk to external services, specialized.com, for DNS, maybe your database, your content delivery network, maybe you're using like hosted LDAP or hosted Redis, whatever it is. And it really begs the question, like, how is an operator supposed to reason about all of this complexity? We'll watch that again. So in order to answer that question, I think it's important to ask why. So I just talked about the evolution of the modern data center. And this is where we are. But why did we get there? Right? There has to be some driving reason of why we adopted containers, why they're so popular right now. Why was virtualization a big deal? Why are we using cloud computing? There has to be a reason. Well, our original goal has never changed, at least in my opinion. Our goal has always been to effectively deliver and maintain applications. Whether you're a developer or an operations engineer or a DevOps, we'll talk about that later, our goal is always the same. We want happy customers. And whether our customer is a normal person, like a consumer, or it's someone internal within our organization, we always want to effectively deliver and maintain applications. That's always been the goal. To put it another way, we want to move fast and not break things. Right? So we want to deliver continuously. We want to integrate continuously. We want to test continuously. And if you break that down into the three phases of development, or of like systems management, you have the development, which is done by the developers, the applications engineers, the software engineers. The deployment, which is shared between the operations engineers and the developers, and then the maintenance, which is primarily done by the operations people. So on the development side, the things that developers care about are consistency. Like I want my development environment to be as close to production as possible so that the code that I write is not going to break because of some external constraint I wasn't aware of in production. I want it to be shareable. So I want to be able to give you my code and you can run it, but I also want to be able to run my code locally and show it to you. I want to be able to show it to managers. I want to be able to share it with my team. It needs to be readily available. So I don't want to wait 3 weeks for my development machine to come up. It should come up in like seconds. I should be able to destroy it and recreate it. And that high production parity. So not only do I want my development environment to be consistent with all my developers, but I want it to be consistent with production. And then on the operation side, the deploy side, really all I need to do is bring up some servers, which that's handled by someone else because the acquisition stage is offloaded. All I need to do is kind of start and configure some services, maybe lay down some templates, and then download and run the application. Right? So whether it's a binary or something like a Rails app or a PHP app, I just want to execute it, and now the machine is ready to go. So once it's running in production, there's a maintenance phase. And the maintenance phase is kind of the updating of those servers, whether it's configuration management or updating the applications themselves, maybe reconfiguring, doing things like feature flagging, blue-green deploys, like those types of things. Really, the key components of maintenance, though, are monitoring the health and then orchestrating the complex changes. So a big rollout, or updating the operating system version, or doing kernel patches. Those are kind of the maintenance side of things. So I bring this up because we looked at this a while back and realized that this was the direction that data centers were going. This is the direction that modern computing was going. And we built open source tools for every single component of that stack. So this is like the big picture moment, where Vagrant is like the perfect development tool. It's consistent, it has high production parity. With Packer, you can output a Vagrant box, which is identical to the AMI that you produced with the same Packer run, using those same Chef or Puppet scripts. And then you deploy that AMI with something like Terraform. And then once it's in production, you can use Console, which under the hood uses Surf, to orchestrate those machines, get them talking to one another, do live on-demand hot swapping, dynamic configuration with service discovery. So the first thing I want to talk about is Terraform. So Terraform is no longer our newest project, but it's still one of the youngest. And Terraform's job is to build, configure, and launch infrastructure. It's at its purest form, it's infrastructure as code. So the motivation for Terraform was just like basically what I talked about for the past 10 minutes, which is, given the complexity of the data center, how do I provision resources? How do I acquire them? How do I acquire compute engines? How do I acquire storage engines? How do I configure network? And then how do I get all of those machines to talk to one another? How do I manage the life cycle of those resources? So maybe I want to destroy them, maybe I want to update them, maybe I want to reconfigure them. How do I manage that life cycle? And how do I do that in infrastructure as code? Right? I don't want to run a command, I want something to be versioned and controlled so that the rest of my team can see what's going on. How do I balance service providers providing a core technology with my own data center? Or how do I balance multiple service providers? So maybe I'm on AWS primarily, but I use CloudFront CDN, or I use Fastly for my CDN. They have very different APIs, but I want to manage that all in one place. How do I enforce policy across these resources? So how do I enforce not only security policy, but user policy, configuration policy? And then finally, how do I automate all of that? Because nobody has time to manage 1,000 machines by hand. Nobody should manage one machine by hand. So Terraform's goal was to answer all of those questions. It's to provide a single workflow, whether you're a developer or an operations person or a sysadmin or a DevOps. And that single workflow needs a unified view that provides infrastructure as code. So it's very, very simple. It's describing your infrastructure in a text file. And that text file needs to be changed and iterated safely. It needs to be versioned. It needs to be shareable. And it needs to be capable of very, very complex n-tier intergraph dependencies. But it needs to be simple enough that you don't need a PhD in graph theory to understand how to use it. So this is a Terraform configuration file. And I'm going to walk you through it. If you're familiar with like Nginx config, it looks a little bit like that. It uses a tool called HCL, which is also JSON compatible. So this is a Terraform configuration file that spins up a DigitalOcean droplet with DNS using DNS symbol. So we have two providers that are not related to each other. DigitalOcean, which provides infrastructure as a service, and DNS Simple, which provides DNS as a service. They don't speak the same API. The first block here, the DigitalOcean_droplet, is a type of resource, and I'm giving it the web name. And then everything under that is just an attribute that is dependent on whatever that resource type is. So for DigitalOcean, I need to give it like a name and then a size. So this is 512 megs, the operating system image, and then which region I want to launch in. And then the second part here is the resource for DNS Simple Record. And like DigitalOcean_droplet and DNS Simple Record, these are built-in core providers in Terraform. And I'm just giving it a name of hello and a fake domain, fake name. And then the important thing to look at here is that value. And it looks a little weird. It's kind of surrounded in the $ curly braces. That's a Terraform variable. So what we're saying is this DigitalOcean droplet here is going to be created. And once it's created, it'll have an IP address. It'll have an IPv4 and an IPv6 address. And the DNS, like the DNS record, needs to know the public IP address of that instance to be able to forward the DNS requests. So what we're really telling Terraform here is that the DNS Simple Record depends on the creation of the DigitalOcean droplet. And Terraform builds a graph based off of these variables and knows what order to build these machines. So if you have a Terraform configuration that spins up 100 machines, Terraform calculates all of the interdependencies for you. It does as much in parallel as it can, and then it waits for responses from other variables before it launches into configuration. So it makes sense that you can't configure your DNS provider to point to an instance until that instance has an IP address, because you don't know that ahead of time. Well, Terraform kind of handles all of that for you in its core. It's a very human-friendly configuration. It's very easy to write by hand, but it's also JSON compatible. So if you're used to using something like CloudFormation, you can still use JSON. It'll be consumed as JSON. You can use machines to generate Terraform configuration. The human-friendly config is VCS-friendly. So if you're using Git or SCM, the diffs are super, super nice. You can see exactly what resources were changed. But most importantly, it's your entire infrastructure in a single text file. So like if your entire infrastructure was one DigitalOcean droplet in a DNS record, you just capture that in a text file. For larger infrastructures, we have this notion of modules, and you can break Terraform out into smaller modules that are controlled by different groups in the organization. But at the end of the day, you're actually describing your infrastructure as code, and it's versioned, and you get all of the benefits of application code, but these are with these servers in production. So I talked a little bit about Terraform's graph. I want to dive into that a little bit more. So this is the Terraform graph for what we just talked about, the last resource. And you can see the dependencies. So you have to read this from the bottom up because it's a dependency graph. So the DigitalOcean provider uses, the DigitalOcean droplet web uses the DigitalOcean provider, and it needs to be created in order for the DNS simple record to be created. In a very large, complex infrastructure, you can actually see acyclical cycles in the graph. Terraform graph is a command. So if you actually want to see all the dependencies in your infrastructure, you can run Terraform graph, and it'll show you all of the nodes that depend on each other. Terraform itself is actually pluggable. So one thing we realized super early on is that we can't build APIs for every single cloud provider that exists now and will in the future. So it's open source. Everything we talk about here is open source. But if you don't want to wait for your pull request to be merged, you can actually write your own provider. Providers provide a single integration point for you to manage a resource, or for Terraform to manage a resource that you own. So you expose or provide a resource. So AWS_instance, DigitalOcean_droplet, DNS simple record. These are all resources that are in Terraform core. They all support a CRUD API, so create, read, update, and destroy. For some resources, that doesn't necessarily make sense. So a lot of them are like no-op operations. So if a destroy operation doesn't make sense, you still have a destroy operation. It just doesn't do anything. It's a no-op. It's super pluggable. So whether you're just waiting for your pull request to be merged into Terraform core, or if you have some really weird one-off use case that you don't want to give back to the community, you can plug that right in. You don't have to worry about maintaining it. You can keep it internally, import it as a module, whatever you want to do. So in this way, Terraform provides us with this layer cake style infrastructure. So from the bottom up, it doesn't matter whether you're on physical machines or containers. Each component is managed by Terraform, because you can deploy a container the same way that you can deploy a physical machine. And it all happens with one command. So Terraform apply. And if you describe your infrastructure in a Terraform configuration file, all you have to do is run Terraform apply, and it does everything for you. And if that's a little scary, you can run Terraform plan, which will tell you exactly what it's going to do before it does it. And then you can say yes or no. Terraform has a lot of support for many popular providers, including like Console, DigitalOcean, Google Compute Engine, AWS, Atlas, etc. It's growing every day. Like I said, it's open source. So if there's something on there that you'd like to see, you have the ability to change that. So as I said before, Terraform plan is the kind of the no-op, the dry run mode. But I'll talk about why it's better than any other dry run mode out there. So Terraform plan tells you what changes it's going to make. So this is the result of the Terraform plan from the previous configuration file for the droplet and the DNS simple record that I showed before. You'll notice that each resource has a little plus sign by it. That means it's going to be created. If it's going to be altered or updated, it'll have a little squiggly tilde. If it's going to be destroyed, it'll have a minus sign. For the attributes that I gave, they appear in the list here. But you'll also notice that there are these computed attributes. So there are things that Terraform doesn't yet know. There's no way to know what the IPv4 address of the instance is yet. And the same thing is true for the DNS record, and then you can see that we have that dependent value. So Terraform Plan shows you what will happen. You can explain certain actions. That's getting a little bit better. But most importantly, you can save the output of that plan as an executable plan. So what that means is that if you run Terraform Plan and you're happy with the output, you can save that plan and execute it later. So even if things have changed, it'll apply that exact plan. So previously, we didn't have any of this. We manually manage resources. So with Terraform, we have the ability to do all of that. But there's still a certain degree of uncertainty. So the last thing I want to end with here, and we're changing colors to make a change, is future ops. So I want to talk about, this is what we're doing now. Right? I just explained how you should manage the data center now. Now I want to talk about how you would manage the future data center. So this is the section of the talk called Future Ops. So how would we manage tomorrow's infrastructure? And it's really simple. The answer is immutable infrastructure. How many people have heard of immutable infrastructure? Cool. How many people think it's like garbage? Oh, yes. OK. Cool. I'm done. So let's talk about mutable infrastructure. With mutable infrastructure, which is what we're using now, with each change, the confidence that that machine is has parity goes down. So every time you run configuration management or production, the differential of that machine increases. Similarly, the consistency of that machine to its peers within the cluster digresses. So over time, it's possible that, or as I said last night in a conversation, if you have 10 production nodes and you run Chef Client or Puppet Apply on 10 of them and it fails on one, 10% of your infrastructure is now different, which means 10% of your traffic receives a different machine, a different database, whatever that configuration was. With immutable infrastructure, we push all of that to build time. So production never sees non-parity. So it's 100% consistent across the board. Immutable infrastructure is faster. Deploying an AMI or bringing up a compute engine is incredibly fast. It's seconds. It allows for greater parity because every time we deploy that AMI, it's the exact same AMI. The problem is that it needs automation in order to succeed because building machines by hand is incredibly painful, very, very difficult. Well, that's where Packer comes in. We thought of all of it. Packer provides machine images. So I know what you're thinking. Yuck, like machine images, golden images. In the past, DevOps has been traditionally against golden images. But they used to be the way. So why did we change? Well, golden images used to be this quarterly unchanged and blessed image that was produced by like 3 people within the organization. And getting changes in was very, very difficult. It was slow, it was frustrating, and the tooling was in no way near the maturity that it is today. It would take weeks to build this golden image, and it would take a whole quarter to get a change in. Well, modern configuration management like Chef and Puppet, Ansible and Salt changed all that. We don't have to manually configure machines anymore. So now we can use automated machine images. To put it another way, this is my favorite quote of the entire slide deck. Ops without machine images is like applications without binaries. If you're not compiling your infrastructure at build time, it's the same as compiling your application in production. So what do I mean? If we look at an application lifecycle, maybe this is a Go application or a Java application, you have your source code and you have a binary. And you click the little compile button in Eclipse or you run something on the terminal and you get a binary. And it pulls in various libraries. And if one of those libraries changes or is incompatible, the binary fails to build. And that never reaches production, right? It fails in continuous integration, it fails in Jenkins, whatever. Well, with the mutable server lifecycle, you still want to acquire a new server, and you have to put all of these things on it. So you have to put on packages, network, configuration management. But if any one of those things fail, you now have a bad server in production. So if you were trying to update a package, and for some reason that package isn't incompatible, now all of a sudden your server's in a bad state. But it's running in production. It's receiving traffic. It's performing a duty. The network is unreliable. CM changes. All of these lead to failures in production. So the machine image lifecycle for the immutable infrastructure is very similar to the application binary. We're taking a new server, and we're bringing it to a ready state. Well, how do we do that? We're kind of cheating, because we're taking all of what we did normally in production, all of the configuration management, all of the packages, all of that, and we're doing that at build time. So the immutable infrastructure movement, in its purest sense, is really just changing where we configure our machines and how we produce the output. So instead of acquiring an EC2 instance, provisioning it every time, we acquire an EC2 instance, we provision it when it's not receiving any production traffic, we configure it as we need, and then we output that as its own AMI. All we're doing is pushing the configuration that you already have using Chef or Puppet or whatever you're using into build time. Any failures that occur never happen in production. So in this way, immutable infrastructure embraces configuration management. Packer uses Packer templates. Right now they're JSON. They'll support HCL shortly. So you just define your whole machine. You define the steps that you need to take to create your machine. And whether you're going to use something like Bash inline or you want to use something more powerful like Chef or Puppet, that support is all built in. So if you're already using Chef to manage your infrastructure, you can take those exact recipes and cookbooks and just apply them at build time. The important part is that it transitions any failures that occur in the acquisition of the machine or the configuration of the machine from runtime to build time. It enforces that parity with staging as well. So Packer can output an AMI, and you can use that AMI in your staging environment the same way you can use that AMI in your production environment. And it's 100% parity. It's the same machine. You could even checksum it if you wanted to. And Packer can even output Vagrant images. So in the same Packer run, you can output the production AMI that'll also be used in staging, and a Vagrant box that your developers can download that's exactly the same as production. So what does the future look like? Well, it's really simple. If we break it down into kind of 3 tiers, development, operations, and production, an operator makes a change to Packer. Maybe they update a configuration, whatever. Packer runs. Packer produces output. It produces a Vagrant box, and it produces a production artifact, maybe an AMI, DigitalOcean droplet, OpenStack OVF image, whatever your production is. In this example, I'm using an AMI. The developer, who has already been working, just runs Vagrant box update, pulls down the latest version, and now he or she has the exact copy of production that is deployed. And when that software engineer or the developer wants to deploy, their code was built using the exact AMI that was in production. So in that way, the deploy is effective. Well, I don't want to say the deploy is not going to fail, but the chances of the deploy failing are significantly lower because it was coded on the exact same machine that is running in production. Same operating system, same configuration, same users, same services, same everything. So this is what the future looks like. This is how we're going to manage the modern data center. At least this is how I think we should manage the modern data center. So with that, I do want to leave some time for questions. I went fast at the end because I wanted to leave time for questions, but that's it. I think we have one right there.
I would like to ask you about this immutable infrastructure. If you have a configuration that is fully templated and it's quite dynamic, what can you do with this? You have to have some sort of management on production.
So you mean it has like dynamic values? Yeah. So immutable infrastructure in the 10-year definition ago was only something that was achieved by like military organizations, and you would sign the memory and you would say that only these machines can run. That's not what we mean when we talk about immutable infrastructure today. So what you're really talking about is service discovery or on-demand configuration. So if I spin up a new EC2 instance, how does that EC2 instance know where my Postgres cluster is? That's what console does. So console exposes DNS level queries for services. And basically, you add your Postgres cluster to console, and you tell it this is Postgres service, and then you point your other instances at like postgres.service.console, and console resolves that as DNS and points it to one of your Postgres instances, whichever one is like, it does a round robin right now. And console also supports a key value store. So if you have like configuration, maybe it's a feature flag or something you want to toggle on and off, you can do that right from console. Does that kind of answer your question?
Yeah, so you take away values from like generated templates away to console.
Right. So there's build time templates, things like your web server configuration, and then there's runtime templates. And you would use something like console with like console template, which is a tool that runs on the machine that automatically writes config when it's done.
Okay, thank you.
Thank you. What will happen if there will be a loop relation between a couple of nodes? For example, if I decided to provision backend node and the database node. I need to know the database IP address on the backend and the backend IP address on the database to configure IP tables or something.
Yeah, so Terraform will detect that's a cycle in the graph. So Terraform will look at that and say, okay, I can't solve this graph. It's an unsolvable graph. And in Terraform, you can tell it, okay, we'll actually create this one first, and it'll just do extra work. So it'll create the one, create the second one, and then go back and reconfigure the other one. Because there's no way for it to solve that graph. I think the real answer there is if you can push that off to runtime instead of build time, then you can use something like console where they can actually just discover each other. So once the backend node registers, it'll register itself with the console cluster, say, hey, I'm a backend node. It becomes backend.service.console, and that's what's coded in your front end. And basically, you're just waiting for each of them to come up.
So in your example of immutable infrastructure, you're still drawing a distinction between application release automation, so deploying the app, and managing the infrastructure. Is that correct? Because I see a lot of people get those two things really confused and start to try and bake their application into the AMI, and then that is not faster.
Right. Correct. You're right. So I'm making a comparison between how we build application binaries, the same way that we should build production artifact or production AMIs, production droplets, whatever. So the same way that you take source code and you compile it into a binary, we should be thinking of our infrastructure the same way. You take your source code, which is like configuration management, the base kernel, whatever, and you compile that into a binary, which is something like an AMI or a droplet. Does that answer your question?
You still need to have that second mechanism, which is application release automation, that is going to be the mechanism by which you push out your RPMs or your Octopus deploy packages or whichever. So you still have an issue of configuration drift at an application level that you need to be aware of. Right,
and I mean, depending on the size of your application, you can bake it into the AMI, but it all depends on the actual use case. Right, so for something tiny like a little Go service, you could build that right into the AMI. But for something that's like a Rails app that requires lots of dependencies, or like a Java app or something that you can't just like throw down as a binary, yeah, there has to be like application level configuration.
Well, this can be useful. Sorry, this can be useful also when you have to start up load plenty of virtual machines. Let's say if you have some change in your infrastructure configuration, and you have to install some package on each of instances, it will take, let's say, few minutes multiplied by number of your instances. And what we used it for is this way we shorten our launch time of our services, because if you create the AMI with the current version of your instance, you could start up your instances much faster than you would if you had to install those packages manually on each of instance.
Right, because you don't have to wait for the package to download each instance. You download it once, bake it into the AMI, and now you just launch that AMI. Yep.
So I have one question about Terraform, and so my understanding is that actually like Chef, for example, or Puppet, are actually complementary with those technologies, right? So we need Terraform, we need Packer to pack it, but we still need something to document the infrastructure.
Mm-hmm.
So for example, Chef Cookbook. So one thing which usually you have to struggle with in Chef is actually making sure that the cookbook is idempotent, so it like both works from scratch and from the previous like image. So so actually, what's the idea? Should we build the next image from the like latest one, or from scratch, from like the basic image? And if we still need to make sure that the cookbook works both for like raw Amazon image and for our latest image, what's the benefit of creating images, like fixed images?
Right. So if I understand, the question is, do you start from scratch every time and apply the Chef Cookbook from the base operating system, or do you use the old AMI, like the previous AMI as the base, and just run Packer again on it?
Yes, but either way, like Cookbook should work with both approaches anyway, right?
Right. So the answer to that is really it depends. It depends on the size of the AMI that you're producing. If it takes 45 minutes to provision an AMI from nothing, then you're probably better off iterating and using the old one and just applying iterative changes. But at any point, you should be able to go from a base operating system to a final machine, because what if you want to upgrade the operating system version itself? You want to switch from Ubuntu 14.04 to 15.04, like you're going to have to go from a base OS. I guess you could do like an on-disk upgrade, but you're probably better off going from scratch. I don't have a good answer because it really depends on what you're doing. I think your Chef Cookbook should still be idempotent and convergent. I think you may not need to concern yourself with it as much. So I used to work for Chef, and we spent a lot of time in the cookbooks that we made at Chef making sure that they were idempotent, to the point where sometimes like writing out the same file twice doesn't actually harm anything. Right? Creating the same user twice will cause an exception, but if you write the exact same file twice, it doesn't actually cause any harm. And it may be more work to check and see if the file exists and has the exact same content, as opposed to just writing out the file. So a lot of times it's a trade-off. You have to analyze, like, do I need to be idempotent, or is doing the operation again okay? Because sometimes being idempotent actually takes more time than just applying the operation each time, if it's a safe operation, right? So if you think about making your directory, you have to check if the directory exists and then make the directory. But if you just make the directory with something like makedir-p, if it exists, it'll make it. Or if it exists, it won't make it. If it doesn't exist, it'll make the whole path. So in a way, you're actually saving an instruction sequence by using just one command, if that makes sense.
So we think like deploying the image is faster than running Chef on the existing machines. So
yes.
Or is it less risky, or?
So it's definitely less risky, because if Chef client fails, now you have divergent nodes in production, and someone needs to be woken up in the middle of the night to go fix that. But also, pushing that to build time pushes those failures at build time, so you never have bad production artifacts. It's also much, much faster. Spinning up an AMI is really a couple seconds. Spinning up an AMI and then installing Chef and then running Chef. Yeah, and the gentleman sitting next to you, as he said, if you're bringing up 15 nodes, each of those 15 nodes need to download the package 15 times. Or well, each node downloads the package once. So you have to download that package 15 times, and that causes like network latency, et cetera. And whereas with the AMI, you download it once, and then you just deploy the AMI because it's baked in. Okay.
Are you out of time?
I think she tells me I'm done.
Okay. It's a quick one. It's really cool, Terraform. Because you can see the config file with like your whole infrastructure in it, are there any like visualization tools that will visualize like your architecture, I guess, your infrastructure, because you know that it's a droplet, so you can show that as a DigitalOcean cloud, and then you know that you're talking to a database, so you could. Are there any visualizations for the graph yet, or not?
So the only visualization is Terraform Graph, which is just Graphiz. It's what I showed. We don't have the ability. We have the ability. We haven't done it yet. We haven't added pretty little clouds around your DigitalOcean on the graph. It's definitely possible though. It's an optimization that we're still working on Terraform's core, and that's kind of like that's more of like a polish thing, and we're not really at that polish stage yet. So Terraform is production ready, but it may not be like UX friendly 100% yet.
Thank you very much.